I'll speak today about Margulis proof for Borel Harish-Chandra theorem. Borel Harish-Chandra theorem is that arithmetic proofs are lattices. The standard proof is by reduction theory, which is also very nice and very applicable. And Modulus Function is completely different. And quite interesting. So when I was a postdoc in Yale, I had an impression that he's proud of that proof, and this was surprising for me because he has so many fantastic and deep theorems. So I was so special about this. But now, when I read it carefully, it's very impressive and very, very clever. Sorry? So okay, so the proof is in this paper, which is hard to find in the internet. I don't know if it's possible to find, but I have a PDF version of it. It's called Running Walks in the Space of Lattices and Finiteness Volume of Arithmetic Proof. And I will have to look inside at some point. I took notes, but I don't know if it's enough for me. So I'm going to give you a criterion for finiteness of volume and then apply it for arithmetic groups. So, okay, so the title of first part is finiteness of measures and non-divergence and maybe we'll be quick enough. I will give you a proof today that SLNZ is the lattice in SLNR. And next time we'll deduce that every arithmetic group is a lattice in every semi-simple group. The same strategy is for the original proof for Borel Harish-Chandra, but the way it's done is completely different. And so this is done via considering random walks. And actually, also my recent theorem with Tsachik is strongly influenced from the method, although it's a completely different situation. So let G be a locally composed group. And suppose G acts continuously, G acts continuously on some space, let's say locally compact. With the writing is readable, Gil. Okay, it's readable. Locally compact space X. And suppose that there is a measure on X. So mu will be a measure on X, a probability measure. G, let's say some generating measure on G and sigma, a measure on X. G invariant. on X. Okay. At the end of the day, you should imagine it's some generating. So the type of measure that I like to take is the R measure on K convolution. So this is an example. If K is a maximal compact subgroup of G, you can take the R measure on K and then take some Dirac measure on some semi-simple element and do something like that. And then this measure will induce a random walk for every space that G acts on. And our motivation today is to give a criterion when sigma of X, we are going to give a criterion for finiteness for sigma of X to be fine. And then we will apply it to the space X, let's say G mod G of Z, like SLM mod SLM Z, and sigma is the induced measure from R measure. So that's the motivation. Okay, so mu defines a random walk with X. X, it's still readable. Yeah. Okay. So this way for point X, the distribution of the random walk of let's say Gx is given by the convolution mu convolution Dirac measure on X. Is this clear? So this random walk induce some averaging operator. An averaging operator. A mu, which is acting to follow a mu of function f. The point X is the integral over G of f Gx and mu. And it's the same as the integral over X of f of X of f, let's say, of y, the u convolution delta x variable y. And this operator is well defined on LP. The LP of X the sigma. It's actually a contracting operator. Let's look for everything. Between 1 and infinity. And if the support is compact, And it's also defined in the space of continuous function. If compact, then it's also well defined. See.
You always take it to be compact.
We will take it to be compact. Basically, for all application, you can just take the mu that I presented before. So in the paper, Margulis is not very specific. When he doesn't need to assume something, he doesn't assume it. So we have many statements for general measure. But what's important is the application, and for all application, you can consider the mu that I described. And also note that this averaging operator is the average of the following operator. Well, a g of a function is given by f dx. Okay, now some ergodicity condition. Point condition star is that there is no non-constant AG invariant functions there's no non-constant, let me explain it this way, not non-constant functions which are AG invariant for every G in the support. Basically, yeah, I think what it means, it basically means that, okay, we will show some points of that. Okay, it's equivalent, this ergodicity condition equivalently star is say that there is no measurable subset there's no subset y inside x of non-trivial measure such that the measure y positive and the measure of the complement positive, which is G invariant for all G in the support. It's the same condition. And okay, what? And we will always assume this condition. That's Oh, that's one assumption. Assume a U. And the lemma. Lemma 1, because we want to be many lemmas. Let's be a Hilbert space. Like them. Hilbert space. And let A a bounded operator. Bounded operator with norm 1. A most 1, such that A star, the conjugate, has no invariant vector. Okay, you probably know this.
Then like frequency.
Have no invariant vector. It's like the ergodic theorem, you can say. The phenomenon ergodic theorem. Then for every V in V, the Cesaro average conversion. That's the phenomenon ergodic theorem. From form of it, although it's
Isn't the assumption usually that A doesn't have invariant vectors?
well, okay, let me show the proof. Proof is immediate. And usually, okay, for the specific operator that I'm going to use, which are the averaging operator, the conjugate is like the averaging over the inverse of mu, and the condition that A doesn't have invariant vector is equivalent to the condition that A star doesn't have. But okay, so what is the proof? So claim 1. The space, let's say U, which is the image of A minus identity, is dense. In V. This is not necessarily closed subspace, but it's dense. And why? Let's say if W belongs to the orthogonal complement, it's equivalent to say that W, the inner product, W with AB minus V is 0 for every V, right? Which is equivalent, say that A star W minus W is 0 for every V, right? Because we see the conjugate of A minus 1 is A star minus 1. So, and this, which is equivalent to say that W is A star. So if we assume that there are no A star invariant vector, then we get that the image that U is dense.
We don't need this W is something.
W is an infinite vector for the operator. So we find that
Why does that have to be zero?
Central.
Why does A start as
A star W equals W.
Yeah, why?
That's our assumption. A star has no
Has no.
no non-trivial. Yeah, that's my assumption. So this implies. Okay, so therefore it's enough to, since the now since the norm of A is assumed to be less than 1, it is enough. Actually, this is since A is bounded. Since the norm of A is finite, it is enough to prove a statement for V inside U. You see that's this 3 epsilon tree, right? If for every V in U, this average goes to 0, and for every V in V, because you start with V in V, you take some V prime in U, which is epsilon closed, then the average over U are of distance at most epsilon to the average over V. Actually, you don't need 3 epsilon, 1 epsilon is enough. And yeah, so you see that, right?
You do need that the norm is contracted, right? Because if the norm of A is 2, this
okay, yeah.
you need uniform now.
Yeah, here, right, since the norm of A is most 1, yes. So, right, if you agree, I don't need to. Okay, and now, so let's, right, V equals A U minus U.
Why didn't we show? I'm missing something very basic. Why? We showed that W is 0. Why does it mean it's dense?
Yeah, how do you show that in a Hilbert space? How do you show that a subset is dense if and only if the closure, the orthogonal is 0?
Taking the orthogonal twice is like taking the closure.
Yeah, if you want the closure of U is the orthogonal, the double orthogonal.
So taking orthogonal.
Orthogonal is always closed.
Taking it.
Yes. Yeah, the orthogonal of U, yeah, if you want this equals this. So this subset, to say that a subset is everything, is dense, it means that its closure is everything. It's equivalent to say that the orthogonal is. Okay, so we write V in this form, AU minus U, and then okay, you apply the Chazal average. Right, 1/n sigma A n B 1/n sigma A n of A U minus U, choose 1/n A with the n plus 1 U of this lemma. Okay, so this is now the assumption in our case for us we take A will be A mu. And the conjugate of A mu is easy to see. It's A of the inverse measure, which is the measure supported by definition mu inverse of a set omega is by definition mu of omega inverse, where omega inverse is instead called G inverse, where G is in omega. So our assumption is that our ergodicity assumption, our star assumption, is that there is no vector which is invariant under all elements in the support. So for any vector, the vector that we are going to consider a L2 function over X. And okay, you see what. So if we apply it, so in our case, the assumption star that we had before implies that that A mu star has no invariant vectors in L2. By the way, it's the same, I mean, exactly the same proof work with LP or any other P. I didn't use, no, I don't have this star. So, okay, no, I do have star. Anyhow, okay. But enough. Okay, Lemma 2.
Maybe I'm missing something, but it's not trivial that assumption star implies this one. Because the assumption was on every G and now you average.
Right.
Maybe you can assume this one.
No, but no, it is clear. So I don't know, but okay, we cannot argue about clear, but okay, I can basically. It's not completely clear. It's an exercise, but you have a measure. It's by the definition of support and by uniform convexity of the sphere in a Hilbert space. So you have V. You can assume that V is in a Hilbert space and the norm of V is 1. Okay. And now we want to consider a mu, what it does to V. Right? So a mu of V is by definition, it's the integral of suppose that G acts on the Hilbert space, the GV, the mu G. But another way to think of it is you look at the unit sphere, the Hilbert space, and you have this vector V, and then you have a measure which is coming from the orbit. So you have a map from G goes to the Hilbert space of the sphere of the Hilbert space, and it sends G to the point GV, and you push forward the measure mu to a measure on the sphere. Okay. And the fact that that this V is not invariant under some elements in the support tells you that this measure is not supported on this. It's a probability measure which is not the Dirac measure on this. Now, and this is a exercise in Hilbert space that whenever you have a measure on the sphere, if it's not a Dirac measure, then the barycenter of the measure is of smaller norm. So that's because of uniform convexity. So if you do a barycenter of a measure which is not just at one point, you will get something inside of it. Because you will have some mass here and some mass here, and average is pretty small. Yeah, so it is true that this condition implies this, but there is some other.
And L2, you want the non-constant function?
Yeah, I mean, yeah, yeah. So here for V the L2 applied to L2 it's sigma 0, which is the orthogonal to the constant.
In the exercise, in the exercise, you.
Yeah, I need 0, and this by definition is the orthogonal constant. Yes. Why do I write orthogonal to constant and not function with integral 0? Because I don't assume that the measure sigma is finite. If the measure sigma is finite, then it's not exactly the function with integral 0. But if the measure is infinite, then this is everything. And I want to consider this case that the measure is infinite because all the point of what we do today is to give a criterion of finiteness. The second lemma is consequent. First lemma. Let L and K side X be compact set.
Hold on, I'm sorry. If you can't integrate f against a constant, then you can take if sigma is it's not finite, then constants are in L2. So you in any case taking the product of some constant.
Yeah, if sigma is infinite, then there are no constant function. Then the orthogonal to the constant is the orthogonal to the empty set.
Okay.
So 0 is the constant function. That's one example, but it's not empty set. It's a 0-dimensional space.
So
yeah,
sigma is infinite is just L2.
Yeah, sigma. In the case sigma is infinite, then it is L2. Okay, so you have two compact sets. So in particular, they have a finite measure and let A be a positive number. Assume this orthogonicity condition. And we also assume lim sup of the Chuzaro average of the inner product of A mu to the N, the characteristic function of L, the characteristic function of K, is at least K. Then sigma of X, the measure of X, you see where we're heading. We want to give a criterion for finiteness of volume, and this will be the type of criterion. So then sigma of X is most sigma of K times sigma of L divided by how do we interpret this? How do we interpret this condition? So that's, you will see it's immediate from the previous lemma, but it's a wonderful observation. So what we do, we have a random walk, and we start, let's say, the random walk at the random point in L, and see what's the probability that it visits. I count how many times it visits K, and if on average this is positive, then I can deduce that my space is fine. So in a sense, this is some non-divergence criteria. So if there is no divergence, so divergence means that every point will go to infinity, or that its average will be always 0. So if it doesn't happen, it will force my space to have finite meaning.
You assume sigma to be a finite and compact set?
I just assume that no, X is a locally compact space, and sigma is any measure, then I assume that L and K are compact.
But does it necessarily mean that sigma of K is finite?
Yeah.
It's a locally finite measure.
Sorry?
You mean it's a locally finite measure? And
I don't need the name of Borel or
regular.
and there's
I will also.
If it's locally compact second countable, you can just say locally.
My assumption. I also later I will also want this to be Borel regular, which is Radon. So I will not here, but later I will also. My compact. What do I need to assume about sigma? Of course I want to assume that sigma is locally finite. Here it's for this is enough. But for later I will also assume that it's Borel regular. You will see.
So,
yes.
So did you say that this inner product is indeed some? How do you interpret this inner product as a probability? Like in terms of the random walk?
So I have this several interpretation of the random walk. So what is this? What is this? I just look at this term. So what is this? Is the probability that if I start at the random point in L, I will end at the random point. I will end inside.
Steps. After n steps.
After n steps. This you can interpret as the probability that if you take an average on L, maybe that's what we need to do, right? Okay. Okay, so let's try to prove it.
Why do you need the Chazor sum?
Sorry?
Why do you need this averaging over the?
Why do I need it?
Can you just say it's uniformly bounded from below? It's stronger.
But this is
Weaker.
Well, we started with this ergodic theorem, which was about Chazor sum. The first lemma was about Chazor sum. I don't. What do you mean? Why do we?
Maybe you can say like visits the random walk visits K infinitely many times. So
it's more than that, right? It's okay. Let me write a proof. Chazor sum are extremely useful. Why don't you use them? So here's the proof. Sometimes you get better information and you don't need it. Okay, so let's let chi L prime be the projection of chi L to the orthogonal to the constant. So what is the constant function? It's either zero dimensional if the space is infinite measure, or it's one dimension spanned by the constant one. So what is chi of L? So that is.
You mean in L2, right?
Chi of L. Chi of L prime equals chi of L if sigma of X infinite, and it's equal chi of L minus the measure of L divided by the measure of X times the 1 if right?
Yeah.
If this one. Anyhow, I want to work with this function. And for this function, I know from the previous lemma that the Cesaro average goes to 0. Okay. By lemma 1. One over n sum n goes from 1 to n of a u n I L prime goes to 0 in L. How do we interpret it? So this immediately tell you that this cannot happen, right? Okay.
So in the level before, when you said that vectors converge to 0, it's a norm,
Yes.
not weakly.
No, but no convergence is stronger
Yes,
than
stronger, okay.
weak convergence. So in particular, so this implies that sigma, this implies the problem, right? That sigma x is finite, right? Because if it's infinite, then chi of L prime is chi of L, and you have a contradiction. Okay. Let's write it. If, assuming that the measure is infinite, we get that 1 over n, that a, which is positive, smaller than equal to lim sup of 1 over n a to the n chi L chi of k, when this converges to 0, a contradiction. So therefore, the measure is finite. When you apply to finite, so now you know, so this implies that by the phenomenal Margulis theorem, that the Cesaro average of a nu n of chi of L converges to the constant function integral of k, integral of L divided by integral of x times the constant function. And okay, and therefore, when you apply it, and therefore, a less than equal, then
It implies that what? This is what? And it approaches.
I mean, because this goes to 0, it's the same as saying that this is a constant function. When you average it, it's the same. Okay, so it means that this converges to that. But now,
I'm just plugging like the product.
yeah. So therefore, A is smaller than equal, then the limit two, but actually there is a limit of inner product A mu and L by K, which, what is it? It's the integral. It's the integral over K of because this converges to a constant function, sigma of L divided by sigma of X. This constant, why do I denote the constant by 1 and the other? Yeah, one is one by definition of the function X. So, which is sigma of L divided by sigma of X. So the conclusion that sigma of X is bounded and sigma of K. Conclusion of sigma of X is most sigma of K and sigma of L. But actually, the concrete estimates that we get on volume will not play any role anyway. They don't play any role because you will see, I mean, but we will not have any control on the sets that we will choose later. But it's just the fact that it's finite.
Yeah, so we don't need the rest. Just that it's smart.
Okay, for the application, we will not. So this method give no clue about. It doesn't give any way to estimate at the end of probably not today talk, but if I would go faster, it would be at the end of this talk. I will show that SL and Z is of cofinite volume in SL and R, but I will not give any concrete estimate for that one. So, okay, so now Lemma 2. So let K inside X be compact. And suppose that B is a positive number. And again, assume this velocity. The velocity. And also that the measure sigma of the following set, psi, which is a set of all x in x, such that the lim of 1 over n is at least b. Okay, we soon I can understand what this means is positive. Consider all the set such that the random walk, all the points, such that the random walk starting at this point visits K B of them, let's say. The proportion that it visits K is bigger than some positive number. Then sigma of x is finite, and all go right.
Here,
Yes.
it's like you use regularity to say that then you get this limit on the compact set. Like, because this is exactly what, like integrating against the constant function on the whole space, right? So if you look at the inner product from before, then just substitute L to be the X, then
Yeah, the idea is to, okay, we're going to use it from the previous lemma, and basically we will take L to be psi. Except that psi, I only know that it has positive measure, but maybe it's not compact. So inside psi, I will take some compact set of positive measure, the regularity of sigma. There is some positive measure compact set inside psi. And then you call it L, and you apply it to that, and you will. So let's
which is other lemma, if we take L to be equal K, and then
yes.
so then we say this average goes to 0.
It's very.
L to be equal K.
I don't.
If L equals K,
Yes.
so this average will go to 0.
It's not dependent on K. So basically, you have a space which at the end will be some manifold, which you do random some arithmetic manifold, and you have two sets inside, K and L, and then you start a random walk from a random point in K, or let's say a random point in L, and you ask yourself, am I in K or not? So the point is that if the total space has infinite volume, so point will diverge and will spread evenly, more and more evenly, so the amount that you will see K inside L will tend to 0. But it's if and only if. So if the space has finite volume, then L will spread, the average of L will spread like a constant function. So the amount that you will see K is exactly the proportion of exactly, and it doesn't matter if K equals L, it will be exactly the same.
So what did you use the fact that K and L are compact and not just a finite measure?
I didn't use the fact that I didn't use, no, I didn't use the fact, right? Basically, so by the way, there is also a paper by Eskin and Margulis, where, well, they do more or less the same, but specifically for arithmetic manifolds, and basically for them they take the epsilon thick part and they show that a random point, a random walk will come back to the thick part, but it's exactly the same thing. So if you know that the measure is fine, but here, yeah, the beauty of this approach is that yeah, it's if and only if, and you can deduce finiteness from that. You will see on the end of today's talk, at least we will have some criterion for finiteness, which can be applied for every arithmetic.
So my lemma 1,
Yes.
if I take K to be equal to L, that goes to 0. No?
Why? I mean,
Because it's the size of
what do you mean? But lemma 1 was about Hilbert spaces, and you take. I mean,
the vector is psi of A.
the vector is psi of
L.
L. Yes.
So the sum, the average needs to go to 0.
If the measure is infinite,
Mhm.
then it will go to 0.
That's never one said it goes to 0. We didn't say if the measure is infinite.
No, but if the measure is finite, then this vector is not orthogonal. Lemma 1 was to the orthogonal to the constant. Yeah. Lemma 1 was about, we assume that there is no constant function. There is no invariant vector. The constant functions are always invariant vectors. Yeah, so it's exactly that. If this space is empty or not.
Meaning not defined.
Yeah.
Makes sense.
Okay, so the proof is immediate after we understand what is written here is what was before. So let's do that and then go to a break. Let L inside psi be compact. Okay. Then if we look at 1 over n, this on one hand,
So
MKFL?
it's positive and not infinite. If we say positive.
oh no,
I
it
guess
could,
you see
it could,
without it. I mean, L should be.
yeah, sigma. You assume, yeah, sigma is a nice measure.
So L is positive measure itself.
So if it contains M, it's positive. If
See, my assumption is that this set, which is described, which is defined by all points, such that the random walk be oftentimes come back to K. This set has positive measure, but maybe infinite. Inside it, I take some compact set of positive measures. Sorry, compact of positive measures. Positive.
So it's clear that measure of psi is positive, but not that it's finite.
Yes. The assumption is that the measure of psi is positive, but not fine. But not necessarily finite. And I take just if it was finite, I probably could take L to be psi, but otherwise I take L to be inside psi, some compact set. You're right that it's not so important that it's compact. I think we didn't use compacted, we just used that it says, yeah,
For the regularity arguments.
no. If our measure is regular, then we can use compactness. But we did in previous lemma, we didn't use the fact that it's compact. Later, we will use regularity in another way.
So you could, instead of taking this, just take psi, chi of psi, right?
No, you want it to be finite. You want it
Except
to be
that
finite positive.
if psi is infinite volume,
Ah,
then chi of psi is not in L2.
okay, I see.
So okay, so this, by definition, this limit what do we get? So we get that the lim in and a lim in. I don't know that the, so okay, we know by previous lemma then on what then lim in of sigma AU I L A on one hand, so this is at least the integral over L of exactly what is written there. The measure mu to the n dx k d d sigma of x. Okay, that's sum. And the integral over L is sum n goes to 1 n, and again leave in, and which we know it's at least b time. It's at least b times
Maybe mu n convolution with delta x of k is exactly a mu to the n of one.
Wait a minute. So this is
This is by definition, right? It's the operator.
let me not confuse myself. So this is at least sigma of L and B.
I think you are missing an exponent.
Sorry?
This is an exponent.
First sum scalar product. Upstairs.
But the mu. Yeah, thank you. Let me just see that what I wrote is correct, and then ask a question. But yeah, I think this is correct. Okay.
No, maybe the quality is on the other way. No. But L is the subset of psi, then with the condition of psi.
No.
It's what happened.
But you need to put the sum inside, do an inequality, and then.
Now, I want to apply the previous level. Just okay. Okay. This implies, let me now by the previous lemma.
Function. Out of it.
That sigma of x is at most sigma of k, sigma of L divided by sigma of L times B. And by previous lemma, with A equals sigma of L times B. So we need to understand this. So why did I, why, actually here there is equality. It's not this equal to that. Because this is just a reinterpretation of the same thing. Yeah, it's better to understand it yourself. At the beginning, when I defined this random walk, I interpreted in several ways, like the averaging operator and also the this convolution, and when you move from one to another, you do this. So that's yeah. Okay, so let's have a break, and after the break, go on. I think at the end of this talk today, I will have at least the volume finiteness criterion. And the next time we will show that it's applicable to everything. Okay, so let's say by
זה עכשיו?
כן.
וואלה, לא יודע.
כאילו, כן, התחיל ביום שני, עכשיו ספציפית עם הרצאה, לא יודע. אני רק יודע שהיא ביטלה לי את הפגישה בגלל.
לא ידעתי שזה, כלומר זה פיזי.
לא.
זה אונליין.
כתבו שזה קיים. לא נקום לעשות GC.
נכון. אורי כתב על זה משהו, נכון? אחד לבקש, לא יודע. אין למה.
אוקיי.
לא צופר.
קרולרי? So let K inside X be compact and G bigger than 0. Actually, item A would be a corollary of the proof, not of the statement. Exactly the statement. So let G inside G and assume there is no non-constant G invariant vector. In L2. And so assume that the measure of the set for X is such that the link in 1/n sigma the number and between 1 and n such that G with the nx to k that is bigger than b. So the measure of that is positive. Then the measure of x is the measure of k. Which is fine. And basically, it's exactly the same proof, even yeah.
That one.
Sorry?
That one.
Curly brackets. One curly bracket.
Yeah.
After the B.
Yes.
This is just taking U to be delta G.
Yes. Actually, yeah, that's a good. Actually, yeah, if you apply to delta G, it's exactly. But it's more straightforward, actually. Yeah. Yeah. A, okay. And part B, it's a continuous version of that. So let H be a one parameter subgroup.
מה מאוד straightforward? כאילו...
Let me say, let me first start the corollary, part A and B, and then say the proof. It's not completely clear to me how we choose the title for the statement, which is Lemma and which is corollary. It's clearly Lemma 2 was corollary of lemma 1, and lemma 3 was corollary of lemma 2. But this, this is called corollary. So let this be one parameter.
So do you assume now it's a legal, or do you mean like in a locally compound to just a homomorphism from R?
One parameter subgroup. I don't assume it's a legal. Only, but okay, it should have one parameter subgroup. And also assume that the measure, it's similar, the measure of all x in x, such that the lim inf when t goes to infinity of 1 over t, the length the time such that h t of each belongs to k bigger than b. Positive. Then again, sigma of x is most over b, sigma of k, and in particular,
So this is pushing the Lebesgue measure in the interval
yes.
to G and letting that mu.
Yeah, but yeah. So instead of discrete random walk, we do some continuous random walk, like one and one.
Yeah, but mu from the beginning you didn't assume to be a discrete, right?
No, mu, yeah, he said.
Mu is already a continuous random walk.
But mu was a probability measure, and okay, okay, to prove one, okay, like Itamar said, so proof of A by the previous lemma, lemma 3 applied to u equals the Dirac.
But you want mu to be generating, don't you?
No, I didn't assume. I do. You equal I didn't assume anything on you so far, except the star assumption. Well, it's the assumption, but now it's explicitly assumed. Later we will. Okay, I think in the next result, I will need the.
This would be the assumption in sigma.
There was assumption that there is no non-constant invariant vector under the support of me. That's my implicit assumption. Here I apply to this mu, which is Dirac G, and that's exactly the assumption.
So you need something similar to H, which
yes. Right. And actually, I think he has some. Yeah, suppose there is no H invariant. He assumed that in the paper, but I think actually for the proof it's not even enough. One parameter subgroup. Let's see the proof. I need some assume some suppose here. What he writes in the paper is that there is no non-constant H invariant vector. But I will need more than that for the proof. So let me write the proof that he writes in the paper. And I think there is actually a small problem here, but a fixable problem. So B. So take epsilon. And let set k epsilon to be the set of all the union of ht k when t is smaller than okay, with some neighborhood of k. And then observe that I read 2 days ago, and I think I repeat exactly what it says, but then there should be some problem. So observe that for t observe that if t is minus n epsilon is smaller than epsilon, and then ht belongs to k implies that h and epsilon, which is h epsilon to the n, so ht of x belongs to k implies this, which is exactly h epsilon to the n of x belongs to k epsilon, right? If you're okay, this is clear, just meditate on it. I mean, to be a time t, if a time t, I mean epsilon, I mean k, so a time almost t, I'm inside this bigger set, because this bigger set allows me to change the time by the epsilon.
I mean, look, you didn't have to be n epsilon, it could be just s. You're just saying that if you change the time a bit, then you're still.
Yeah. No, but why I write that? Because now this assumption implies thus we get that the set of all x in x such that lim in of 1 over n of h epsilon n sigma x let me write it. Yeah. So the idea is that I will, it makes me, allow me to discretize the time. Is k epsilon as measure bigger than, okay. So this implies that lim in of 1 over n sigma h epsilon to the n of x how do I write the event that this set of all x in x such that I want to write the event that h h epsilon n of x. I want to say that it's belong to k. So let's say the rank of that is stupid to write. No, I want to say that this belongs to k. Okay, right. I want to write that this is 1 if it's belong to k and 0 if it's not. I just need the.
I mean, why don't you write the rank of this point of k?
Okay.
The size of the intersection with k.
Yeah, actually, that's good. The size of
1 minus the characteristic method.
okay, the size of the intersection of h epsilon n of x and equals 1 to n intersection with k. Okay, this bigger than b. So this set again as positive measures. So lim if so the set of all x such that lim in yes. This set is bigger than the previous set with
Wait, what was the limit of what?
lim in of
6.
I think
all x in x such that lim in of this intersection, the proportion of time that I visit set k is at least b.
What if h epsilon fixes it?
you want the limit to be at
Yeah,
least
that's the
b.
point. What?
You want the limit to be at least b.
Yeah.
So you can just take h epsilon to be the g for part A and the same.
Wait. So this condition implies this. And this condition and the condition of the lemma. So this is at least this set contains the set that the average with time is with continuous time. And now it's there is some small gap in the paper where it says that this implies by the previous lemma that the measure of x is at most the measure of k epsilon. Sorry, now it's inside epsilon. Okay. Yeah. The measure of k epsilon divided by. Now, why there is a gap? Because of the condition. Because to use the previous lemma, you need to say that there is no non-constant invariant function under the operator h epsilon. And the assumption was just that there is no non-constant invariant function under h, the full one parameter. So there is some gap here. We need to close it. I leave it as an exercise. I mean, or we can discuss it after the talk. So, but yeah, there is some small. I can look in the paper. I don't think
But you don't want to take epsilon to 0? So
yeah, no, now I use regularity. The regularity of the measure of sigma, so this is the first time I use regularity, sigma of k equals lim sigma of k epsilon, or epsilon, but if you can, but as I said, we don't really care about the specific bounds, but yeah, here I use regularity. I just want to check if it says something about this in the paper about this. What's
I mean, for example, if H epsilon fixes a point, I mean,
the point it doesn't matter.
No. But even also fixes a function. I mean, like then the whole group will fix a function because if you take epsilon small enough, then you can take a very center of the compact.
Yeah, that's
right.
That's probably. Okay, so we solve the equation. So it's if yeah, the group acts by isometries on L2. So if there is a fixed point for H epsilon,
epsilon small enough.
If there is a fixed point.
Yeah, you can choose a sequence of epsilons.
Yeah.
It's not fixed.
No, but for okay, let's leave it as an exercise. It's true that it should be elementary, but there is some line to it. But yeah, exercise of the gap. We assumed no H invariant vectors, but we need no H epsilon. Okay, there is some trick like that. I need to think about. I don't want to think too much about it because I want to go to the main result. We still have time. But still, let's discuss the main result and then maybe come. So what do you say? You say that
if I epsilon small enough, then I mean the action of if I have an H epsilon fixed vector, the action of H on the vector will the image will become the orbit will be compact. So if we choose it small enough,
the orbit will be because
you fold up. I mean, it's a circle.
Because if the action is in any case, right?
Yeah.
In any case, the orbit is compact, but so what?
We have a circle. If you take epsilon small enough, then you can take, and you have like a non-zero. You can average.
Suppose this point is
H epsilon fixed.
But then if I look at this,
then the H orbit.
Maybe it's the orbit.
The H orbit, and then but if epsilon is small enough.
No, but for each H epsilon, maybe it's a different vector. There is no uniform continuity.
That's the H orbit circle.
No, but the point is.
Wait. So, wait a minute. I think I see why, but more complicated than that.
No, because then if you take the very center.
No, but maybe if you take a H epsilon invariant vector, maybe there's no uniform continuity of the action. So okay, let's. It's a technical issue. Okay, it's an exercise. Let's leave it as an exercise. We'll discuss it later. Anyhow, I'm not going to use it today.
No, but there is basically you can, if you take, for example, the sequence of epsilon over k, then I mean every epsilon k, like if H epsilon k over k fixes a vector, and also H epsilon fixes the vector. And then you can basically use uniformity. Then you can basically use continuity. Then you can use the continuity.
Okay.
Anyway,
there is some issue here. So let's leave it as a technical exercise. and go to the main goal of today, which is the following theorem, which is again elementary but fantastic result. And so assume that there is a continuous function. So listen, this is a really important, I think, really wonderful theorem. There is a continuous function f from x to the positive, such that it satisfies two properties. First, that it is proper. That is x goes to infinity implies f goes to infinity. Or if you want that the pre-image of bounded set or compact set in X is a bounded set in R. And two is that there is C smaller than 1 and B some real number such that the A nu of F is smaller pointwise than CF. This is the condition. Maybe if you saw this condition in previous talk of mine or on my work with Arya or with Tsachik. So this is a extremely useful condition. So in particular, then the measure of X is fine. That's the finiteness criterion of Margulis. And by the way, such a function, people with genius dynamic call a function with this property with respect to measure a Margulis function. But Margulis, I think, attributes this idea to Lyapunov that it doesn't. So when I wrote a paper with Margulis and Arya about such function, then it didn't call it Margulis function, so we didn't. But in any other paper, people call it Margulis. So a function that satisfies this property. Note that C is smaller than 1, that's the important constant here, and that the function is proper. So if you find such a function, then the space is finite, as finite rule. And basically, that's what the rest of the paper will show, that for every arithmetic manifold, there is such a function. So, and also the construction of the function is nice, but okay, let me tell you.
Do you know of lattices which don't admit such functions?
No, yeah, I will discuss the application after. So let me prove this theorem, and then we discuss some application. So actually, yeah, in a sense, in my paper with Arya and Margulis, we showed a very natural function which works for all lattices. This function is basically one of the injective derivatives. But okay, I'll discuss it. Let's first give a proof. Okay, so what's happened when you do the function f, when you do n times, F. So basically, when you do one time, it's smaller than CF plus B. When you do two times, you see that it will be at most C square F, CB, B. And then if you do A to the N time, you will see that it will be at most C to the N F plus B divided by 1 over C. Right? And I call this constant B prime. Okay. Now I don't want to erase that. And, but I will need a bit more space. So this is constant B prime. Well, B prime is B C. And now let's define a function. Let's define a set if K will be the set of all x in X such that the lower average in let's say sub of 1 over n yeah, of 1 over n sigma of A F X is, let's say, smaller than 2B.
Are you assuming B is positive?
We can take it from, I mean, of course, I mean, if it's negative, then replace it by 1. I mean, yeah. Yeah. We're in better shape. It's B is equal to number. So we have this, and now what about the complement? The complement of K. I claim that it cannot be too large. Bounded by the limits of the integral is bounded by 1 over 2b, the integral over x of somewhere I need to leave. So 1 over n sigma n mu f, and let's say here. Here I can actually take a limit because I know it's a big, and this is smaller than 1/2, right? Then the limit of the integral of c to the n f plus. Yeah, claim that it is smaller than beta b prime divided by 2b prime, which is 1. Let me write it in its let me write it in his language. I mean, so no, sorry. I was confused. Because he defined, it's much simpler. Defined K is the compact set. It's all x such that f of x is smaller than 2b. Okay. Now it says that mu, the M convolution, Dirac x for every x in x, this convolution, I count how many times, but I consider when is it inside that the complement of K. Okay. So that's at most 1 over 2b prime, the integral over g of f of gx d mu and g, which is at most c to the n f of x over 2b prime plus 1/2. And this goes to 0 for every x. Hence, for every, so this implies, okay, this, you agree with that? I want to see,
What goes to 0? The whole thing.
yeah, I want to see the distribution. So this, what is written here is exactly, it's exactly the integral of f over x with respect to d mu convolution n convolution delta of x.
So is it, it's 2b prime or 1 over 2b?
What?
Should it be 2b? Like f of x is greater than 2b prime?
In the complement, f is greater than 2b prime. So if I want to measure the measure of the complement is 1 over 2b prime. It's the measure. It's the measure of the characteristic function of the complement. Over the complement, f is bigger than 2b prime. So that's why the inequality. And over the complement, over the set. In this set, f is bigger than 2b prime by definition. So that's why this inequality. And this maybe, yeah, just have in mind this equality between these two formal. Okay, let me. I need a space, so I will erase that. And it's one line. So this implies that for every x, we have that the lim inf and n infinity of 1 over n some okay now. At least the lim inf of mu and delta x. Okay. When n goes to infinity, no? Which is at least 1 minus lim sum of mu to the n delta x of the complement is bigger than half. Yes, so you see by the previous lemma, by lemma 4, I think it was lemma 4 or lemma 3. Actually, it implies that sigma x is 2 times sigma k. That's it's very simple and very elegant and actually, yeah. So that's a criterion to prove that the space is finite. A space is finite measure.
It's not necessary in general for just a locally complex space to measure. Is it necessary?
It's specifically to the case where you have a random walk, like you have a group acting, and usually it's not so easy to prove that there is a probability measure on G and a function and a Margulis function.
But if there are, if there is a probability function, a random walk, and everything but Margulis function and X is a finite measure.
So usually it's, yeah, I think once you find a Margulis function, you're in good shape. But
No, I mean if you know you have a nice random walk and that X is a finite measure, do you have always Margulis function?
I don't.
Yeah.
Maybe. I don't know what to say, but about this. But let me just. The theorem was if X has a proper Margulis function, with respect to mu, and mu satisfying now the algorithmic condition, then the volume of X is finite. That's the theorem. And Margulis function was a function, Margulis function, but let's define it. Is a function f from x to the real, the positive, such that there is c smaller than 1, that's important, and some constant b in R, usually positive of course, such that the convolution of f, okay, call it a mu, the averaging operator at any point it's smaller than f cf. This is the definition of Margulis function. If you find a Margulis function, if you find a proper, usually you don't assume that in the definition of Margulis function, but if you have a proper Margulis function, then the space is positive. And let me just finish this lecture with telling you about my work with the Arya and Margulis.
Sorry, where did we say it was proper?
to say, I wanted to,
K is compact.
yeah, that K is compact, the K is finite. So with Ari and Margulis, we show the following. The discreteness function so I of a subgroup gamma is a subgroup of a G, it will be the supermove R less than 1, such that the ball of radius R around the identity in G intersect gamma trivial. That's the discreteness function. So you fix some metric in G, and with respect to this metric, you can define a discreteness function of G. And you fix some Riemannian or fix some metric if it's a legal. And the theorem with Ari and Margulis in a recent paper is if G is semi-simple, there is delta bigger than 0, which you can compute actually. We can estimate such that the description function to the minus delta is a Margulis function. It's a Margulis function on the space X of all discrete subgroup of G. So this is a locally compact, with the Chabotti topology, is a locally compact space. On this space, there is one function which you can compute, which is a Margulis function for all yes, on this space. So in particular, for every gamma, if you look at the conjugacy class of gamma or on G mod gamma, you get a Margulis function on G mod gamma just by the discreteness function. For every locally symmetric manifold, you can interpret it in terms of inductivity radius of the locally symmetric space, and there is a Margulis function that works for all. So once you get a manifold, all you need to check is whether this function is proper. If it's proper, the volume is fine. If it's not proper, it's infinite. So that's a consequence of our work. So now
Is this for discreteness?
Yeah, it implies this weak uniform discreteness, but yeah, with an effective bound.
Is it also non-Archimedean?
Yeah, it's true for
Here the Margulis function takes values also with infinity, which is no problem. Like when you said R positive, you allowed infinity, right?
Yeah.
But you need it to be algebraic. You can just take a product of simple.
But yeah, it's. I wanted to say that because okay, this is a recent paper you can find on arXiv, and it's explicit. We can't compute this delta, and it works for everything, but for every semi-simple group. The thing is that Margulis didn't do exactly that, but his proof is much more elementary. We'll see next time. So the goal of next time will be to construct for every arithmetic group. We'll start with S and Z. We construct a Margulis function, and he did it. So our paper is a bit long and technical. So his proof is in some sense more clever and so we'll see. So now we have a criterion for finiteness of volume, and next time we want to construct
the main difference between Margulis is there he takes a particular gamma and constructs a Margulis function for there, and here you construct a Margulis function in a sense on G. That's kind of goes to all that.
So I actually I don't know exactly. We will see. I still don't understand. I understand every step in his proof, but not good enough to understand the difference. I mean, I see the difference. It's completely different story. So you will see he considered the space of all lattices in Rn. G acts, you have a representation of G like SLN R acts on Rn, so it acts on lattices in Rn. You can identify SLN R mod SLN Z by the space of unimodular lattices, and he construct a function there. But he doesn't only consider the shortest vector, he also considers shortest vector in wedge power, and he considers several functions, he looks all dimensions at the same time. It's not clear to me that you cannot simplify it. Maybe you can simplify it. You get some very nice function. Okay, you will see it next time. So I don't really understand. Yeah, you will see it. Okay, so.